constants are really cosmic accidents. And all these possibilities, like Pauli tried to calculate the fundamental constant, seem to be useless. They're just accidentally chosen by the Big Bang and would be useless to calculate the fine structure constant. Or the lambda sub c cannot be calculated this way. So that might be the right picture for the fundamental constant. So maybe I'm right, maybe I'm wrong. So thanks a lot for your attention.
I'll admit my sinful admission. So after CERN and spending 4 years in California, he returned to CERN, and then a year later became a full professor in Wuppertal, and then a year later in Bern, and 2 years later landing in the Sommerfeld chair, or the chair that Sommerfeld he mentioned earlier. That was the
Sommerfeld is my predecessor.
The chair that Sommerfeld once
for that reason, I like to speak about the fine structure.
Right, I get the point. Okay, so the talk is open for questions.
Hello, it is a very impressive talk. Yeah, and I'm very curious about the quasar experiment, and they claim that they saw a difference in the fine structure constant. But I'm very curious about that. Can we exclude the possibility that the fine structure constant is not changed? That it's not. Yeah, it's the same.
No, it's not excluded. In fact, there's another big experiment done by Russian physicists in Paris. They're living now in Paris. They did another experiment. The errors are still large, but they do not find the time change. So it's not yet completely clear. And Art Wolf from San Diego, together with Webb, would like to do another experiment at the Keck telescope in the future. So this is now still open. It's not yet clear. But if Hensch is correct, in Munich, he finds now a time change of lambda sub c in a time of about 3 months. He does an experiment in January, repeats the same experiment in April, and he sees a time change. But so that would be an interesting result. Also, Reinhold in Amsterdam claims that his experiment is correct, which again sees a change of lambda sub c. Now, if lambda c is changing in time, then I would not be surprised if the fine structure constant also changes in time. So it might be here. Theodor Hensch claims he can improve his accuracy by another 3 orders of magnitude in the next 4 or 5 years. In that case, if that is correct, he could also see the change of the fine structure constant per year with a small error. And again, within a period of 2 or 3 months, a very short time. So we have to wait until this comes out. For the time being, you can still live with the assumption that the fundamental constants are really constant. But on the other hand, as a theoretician, I would feel it funny that these constants are not changing in time. Why not? There is some check-up. Also, the fine structure constant, like other constants, could change also in space. So people have looked at different galaxies very far away, whether there's any effect. And it seems, so for the time being, that there was nothing found. So even not on the level of 10 to minus 15. So there could be a time change, but not or very little space change.
Any other questions?
This is a little bit more philosophical question, and it's about if the constants are changing, does that mean there are other new theories that can describe these changes?
Yeah, the theories on the theoretical side, very little is known so far. Witten claims that in superstring series you get such a time change. I never looked at it in detail, but maybe he's correct. But apart from this, I have no idea. We just have to see from the experiment whether there is such a time change before we get into a lot of theories which might be wrong at the end. The theoretical exploration would be very, very difficult.
Thank you.
From the experimental evidence used, I'm an experimentalist, and 3 and 4 sigma effects we have seen in experiment all the time.
Yeah.
So you even showed, the highest effect that you have been showing was from the quasar experiment. I think it's around 4 sigma, but when I look at the data, and also when I look at the other information you gave, I wouldn't go crazy thinking that there is an effect, a significant effect there. To me it looks like there's no strong evidence. Of course the change may be actually there. But my real question is why you said something about the Higgs boson. From the Higgs boson side, indeed it may not be the standard model Higgs boson, but there is a very strong experimental evidence that there is something there that has all the properties of the Higgs boson. So I wonder why this is not a constant, whatever it is, if it's not exactly.
No, it's a constant. Tomorrow there is a conference here in south of here, where we speak about my interpretation of this boson. And it's not a Higgs boson, but an excitation of the W boson. And I don't believe that there is a Higgs boson. The Higgs boson in the standard model doesn't really explain anything. You can use it to introduce the masses for the weak boson, but you cannot calculate the mass of the weak boson. Now, in the standard theory, also the mass of the electron is coming from the coupling of the Higgs boson with the electron. It's a bit crazy. I cannot. If that is correct, we would have no way to understand ever in physics the mass for the electron or the mass of the up quark and all these many, many constants related to the Fermion masses. And I cannot believe that this is the case. I just don't believe that there is a Higgs boson. So I think that the Nobel Prize for Angler and Higgs last year was a little bit too early. They should give it back. They shouldn't spend the money so far. Also, it's a bit, the other people like Kimmel didn't get the prize. It's the same thing. It's a bit funny.
Okay, further questions?
You mentioned the time change of lattice sigma imply energy non-conservation, but could a underlying theory that's actually energy conserving?
No, we are based here on cosmology. And in cosmology, like in general relativity, the overall energy is not conserved. In fact, you cannot define any energy at all. So, and these very small time changes are related to cosmology, I think, at the end. So in that way, they can be understood. It's not a Minkowski space-time where you have a definite energy. It's a general relativity to Riemann space, and things are more complicated here. So there's nothing wrong with the mass of the proton changing in time slowly. I think that's okay.
So, last question? Okay, then. Oh, okay.
Sorry. There is a constant that I'm very interested in many people. It's the cosmological. Why this is not a constant in your
No. You could, it would be the 29th constant. And you can introduce it. I didn't want to go into too much in cosmology here. But in principle, you can also introduce this constant. And also, I didn't include constants related to the dark matter. That's another constant. So the 28 number, the number 28 I have is the minimum number. You probably have more. But I didn't want to go too much in detail. I just like to mention those which are definitely there in the standard model. And not these exotic things.
Okay, let's thank Professor Friztsch again.